Let's try to visualize the effects of variant-covariant matrices sigma on the shape of the bivariate Gaussian distribution. So these are the plots for different sigma values, and the choice of sigma affects the orientation, spread, and correlation between the variables x and y in this distribution. And we use mean vector mu00, which is center of the origin, as our example. In the first scenario, sigma 1 is equals the matrix with rows, first row 1, 0 and second row 0, 1. So it is uncorrelated variables with equal variance. So for uncorrelated distribution, it have axis aligned contours. This distribution is symmetric around the mean 0, 0 with equal variance in both x and y direction, and the contour lines are perfectly circular, which indicating that there's no correlation between x and y. In the second scenario, sigma 2 is equals to matrix with rows. The first row is 1, 0 and the second row is 0, 4, which is still uncorrelated distribution but have axis aligned contours. So these uncorrelated variables with different variance, the spread along the y-axis is larger due to it has a greater variance, which is 4 compared to 1 along the x-axis. So these contours are elongated ellipses still aligned with the axis, indicating that there's no correlation but different levels of variabilities in each dimension. In the third scenario, sigma 3 is equals to matrix with rows. The first row is 1 and 0.8, and second row is 0.8 and 1, which is correlated distribution, which shows the tilted contours. This equal variance with a positive correlation coefficient 0.8, which result in a tilted elliptical contours. So this tilted, which demonstrate that as x increases, y is tend to increase as well, which is the characteristic of positive correlation. In the fourth scenario, sigma 4 is equals to matrix with rows. The first row is 1 and negative 0.5, and second row is negative 0.5 and 2, which is a correlated distribution, which shows the tilted elliptical contours. So in this setup, with a negative correlation and different variance, then compared to the positive correlation case, which led to a tilted elliptical contours that tilted in the opposite direction. So this negative correlation means that as x increases, y tends to decreases. The variance of each dimension determines the stretch of the distribution along that axis, and these visualizations highlights how the covariant matrix sigma controls the shape and orientation of the Gaussian distribution in a two-dimensional space. So the choice of the sigma directly influences how the data points are dispersed around the mean and how the variables are related to each other. These are the plot of bivariate normal distribution for different values of mu, which is the mean vector, while keeping the covariance matrix sigma constant. The covariance matrix sigma is sigma equals the matrix with row 1.5 and 0.51. The covariance matrix implies that these variables have a standard deviation of 1 and correlation coefficient of 0.5. This is the distribution for three different mean vectors. Mu1 is equals to vector 0, 0, and the peak is at the origin, which indicating that the highest density is centered around 0 for both variables, and there's no shift in these means. And mu2 is equals to vector 2, 2, which means both variables are positively shifted, and the peak is shifted to the point 2, 2, which indicating that the mean or the expected value for both variable is 2, and mu3 is equals the vectors negative 2, 2, and so the peak is at negative 2 and positive 2, which is showing a negative shift in these first variables, and there's no positive shift in the second. The center of the contours shifts according to the mean vector. The ellipses formed by the contours, which reflect the covariance structure, notably by the possible correlation between the variables as indicated by the orientation of the ellipse. So let's talk about the significance of the mean vector. The mean vector mu in this bivariate normal distribution is directly controls the location of this distribution center. So changes in mu translate the entire distribution but don't alter its shape or orientation, which are governed by the covariance matrix sigma. So this demonstrates how the probability mass is distributed around the mean in this multidimensional space, with the covariance determining the spread and correlation between the determinants.